Hello, I'm Terry, and this is my science presentation. First, we're going to talk about reaching orbit on Earth versus Jupiter. And my question here was, can humans achieve spaceflight from other worlds? Okay, for some background information, Jupiter has a lot bigger mass, as you can see here. And therefore, its surface gravity is going to be a lot bigger because mass is related to gravity. Gravity is how masses attract each other, and a bigger mass means more gravity. So to test out my question, I ran some simulations in Kerbal Space Program, which is a flight simulator. And the only difference between these two launches here are the amount of gravity. So here they are launching right now. On the right, I had to use a lot more fuel to get the same amount of acceleration because I was in Jupiter's gravity. So if we compare the ending stats of these two orbits, they have about the same height and the same shape. They're both like ellipses. And on the right, with Jupiter's gravity, we can see here that the speed I need to get into orbit was much higher than, let's say, the one for Earth's gravity. Alright, simulations are cool and stuff, but we need to talk about real-world statistics. How about the Saturn V rocket? So the Saturn V rocket was able to get to the moon and back with Earth's gravity, which makes it very space capable in my opinion. Now, it had a thrust-to-weight ratio of about 1.2, which means after it started, it accelerated up from the ground on Earth at about 1/5 the acceleration of regular gravity. Now, as a reminder, Jupiter has 2.5 times the gravity, so therefore the rocket wouldn't even be able to get off the ground in Jupiter, so that wouldn't work. Here are the main problems. Gravity is too strong for most spacecraft to even take off on Jupiter. So we would need to have really innovative launch mechanisms, like a slingshot or something. And even if we could take off, humans inside would be subjected to extreme g-forces, at least 2.5 g's, which is how much gravity Jupiter even has. So that would make it really difficult to fly humans in or out. So all missions would probably be robotic. As a side note, the Cassini and Galileo missions, among others, were actually able to fly in close to Jupiter and then fly away. But that is only because they never touched the ground and they came into the Jupiter system at a very high speed, which let them kind of slingshot their orbit around and then escape. Alright, next I want to talk about air resistance. How can air molecules keep things from falling at the same rate? On the particle scale, we can see that an object moving through an atmosphere collides with more particles in that direction because it's moving in that direction. And particle collisions, when two particles collide, they bounce away from each other with opposite vectors. So basically, particle collisions push back on both objects colliding. That means that an object moving in a direction will experience more particle collisions in that direction and then have a force pushing back on it from that direction. Let's talk about drag. From the formula for drag, we can see that drag is proportional to velocity squared, drag is proportional to cross-sectional area, which is how big the object is from the front, and drag is also proportional to density of the fluid. So these three variables all contribute to increasing drag, but velocity would contribute the most because it's squared. So here's why parachutes work. Parachutes work by increasing the cross-sectional area of the object that is moving, which means that its area increases and therefore its drag increases because drag is proportional to area. This only works if there's an atmosphere, of course, because drag is proportional to density of the fluid, and if there's no atmosphere, then there's no density. Even still with all of this, there's still something called terminal velocity, which is the point at which an object that is falling or accelerating, the force kind of equals with air resistance, and it has a net zero force. All right, thanks for watching.